Hi, in today's video, we'll have a look at simple regression. In previous videos, we looked at the correlation coefficient, which indicates whether two variables, let's say x and y, are associated with one another. But the thing is, it doesn't tell you how much a 1 unit increase in x affects y. If we look at the particular graphs here, we can see that they actually have exactly the same correlation coefficient. So the correlation coefficient between x and y1 is exactly the same as the one between x and y2, but we can see that the relationship between x and y1 is very different from the one between x and y2. In this case, the slope seems to be relatively small, so positive, but not very large, whereas in this case, the slope of the line of best fit would be much steeper. So we know that correlation is not enough to tell us everything we want to know about the relationship between x and y. The other thing is that when we compute the correlation coefficient, we do not make any assumptions about the direction of causality between x and y. And actually, the correlation between x and y is exactly the same as the correlation between y and x. It's a symmetrical measure. And if you look at how it's calculated, you can see that it doesn't make any difference. Yeah, so remember that the definition of the correlation coefficient is the covariance between x and y divided by the standard deviation of x times the standard deviation of y. Now, this is exactly the same thing as the covariance between y and x divided by the standard deviation of y times the standard deviation of x, okay? Because the covariance also does not depend on the place of x and y. Now, to conduct a simple regression analysis, we do need to make an assumption about the direction of causality. So for instance, we may assume that y is caused by x, okay? And that is very often the assumption that we're going to make, at least in how we refer to the variable that is being caused and the one that is causing. So we will call y the dependent variable because it depends on another variable, which we'll call x. And x will be the independent variable. There are different ways in which y and x are being called in the literature. Sometimes you will see that x is called a regressor. Sometimes you'll see that y is called a regressand. I prefer to just use dependent variable and independent variable. Now, the mathematical relationship linking x and y is called the regression model. In the simple regression model, we assume that the relationship between x and y is approximately linear. So that's what you can see here between x and y. It seems that drawing a straight line through the data seems like a relatively sensible idea. Okay, and we can see that it does not fit the data perfectly. Some are above the line, some are below the line, but overall, as a sense of the general tendency, is relatively good. Now, mathematically, how do we represent a line? Now, you may remember that the way we represent a line in mathematics is as follows. So y is equal to alpha plus beta x. Okay, that's the way you represent a line. Now, in this case, we have to add an extra term, the ui, which is the error term. So this is the relationship that governs what is happening at the population level. And that's why we use those Greek letters for alpha and beta. But notice this error term indicates that the linear relationship doesn't explain everything. And what is not explained by this linear relationship is basically stored in this term, the error term, right? So we include the error term because we do not expect there to be a perfect linear relationship between x and y. And so everything that is not explained by the model will be in this error term UI. So now let's look at an example. So let's consider the relationship between height and weight among prisoners at the Paisley prison from 1841 to 1883. And as explained earlier, we need to make an assumption about the direction of causality. And in this case, we're going to assume that height determines weight. Okay, so height will be on the x-axis and weight will be on the y-axis. Now, when we look at the data, we can see that it seems like a linear relationship fits the data actually fairly well. Of course, you do not get a perfect linear relationship, and that's always the case when you work with data sets in social sciences, but the relationship appears approximately linear. So here we would say that weight, the dependent variable, is equal to alpha plus beta times height, my independent variable, in other words, my x variable, plus my error term. Now, we assume that the true model for the relationship between height and weight is what we expressed earlier, so that weight is equal to alpha plus beta times height plus this error term. But how do we estimate the parameters alpha and beta? Because remember, this is an assumption about the population model, basically the true model, but we only get a sample. So how can we infer the parameters alpha and beta from our sample? In other words, how do we choose the fitted line for the data? And that will be the topic of our next video.